Today I will tell you a little bit about magnetic topological insulators, quantum anomalous Hall effect, and quantum resistance metrology. Let me start by saying, why do metrologists care about the quantum anomalous Hall effect, or magnetic TIs? As you may know, as of 2019, we have a new system of units, where for the first time in history, all 7 base units are defined based on fundamental constants of nature. And by far the biggest change pertains to the kilogram, which previously was defined based on actual physical artifact. It's called a prototype kilogram. It's a chunk of platinum iridium alloy. It was manufactured more than 100 years ago and was stored in a basement in Paris ever since. And funny enough, so at the same time as the prototype was manufactured, a dozen or so replicas were also manufactured, nominally identical. Funny enough, a couple of times throughout history, people brought all of them together, measured them against each other, and they found that they were drifting. Yeah, you don't want your standard to drift. So that's indeed one of the reasons why right now kilogram is tied to the Planck's constant. And therefore, a way to measure precisely value of h became more important than ever. Okay, so with the new system, one of the big challenges is to measure precisely elementary charge and Planck's constant. And doing it directly is difficult and probably even impossible with the needed precision. So what usually is done instead is people measure 2 different constants, the Josephson constant and the von Klitzing constant. The Josephson, and of course, if you can measure these 2 constants, you can obtain E and H by simple maths. The Josephson constant is measured using AC Josephson effect. It's a basically measurement of Shapiro steps on a large array of thousands of Josephson junctions. Currently, this is the best way we know to get a value of volt. So it's a quantum standard of voltage. And the resistance is measured, of course, using quantum Hall effect, which is the best way we know to measure precisely resistance, to define precisely resistance. Now, one of the goals of modern metrology is to combine as many of these standards into a single universal instrument. And as you can imagine, the AC Josephson relies on induced superconductivity to work, which requires 0 external magnetic field, whereas the quantum Hall effect needs large external magnetic fields. And of course, if you bring these 2 into close proximity, they are fundamentally incompatible. So here, magnetic TIs and the quantum anomalous Hall effect can help save the day by providing quantization at 0 external magnetic field. And one could conceive of building a universal electrical standard this way. Okay, so if we think about studying quantum anomalous Hall effect, for us, the material of choice is vanadium-doped bismuth antimony telluride. We grow these layers using molecular beam epitaxy. This material you can think about as, I need to get used to this. This material you can think about as being a mixture of intrinsically p-type antimony telluride with intrinsically n-type bismuth telluride. The intrinsic doping is a result of intrinsic defects formed during growth, and these defects are notoriously difficult to get rid of. So you grow an alloy to counteract this doping, to make the film as insulating as possible. We also add vanadium to introduce ferromagnetism. Yeah, so if you grow such a layer, you pattern it into a transport device, you cool it to low enough temperature, this is 35 millikelvins, you find that Hall resistance nicely quantizes to plus minus h over e squared, and it traces this rectangular shaped hysteresis loop. This is measured as a function of perpendicular magnetic field. And longitudinal resistance vanishes with the exception of these Shubnikov-de-Haas peaks at the coercive field when the magnetization flips direction. Okay, so before we get to more stuff about metrology, let's talk some physics. And let's talk about dimensionality of the magnetic TI layer, because there are some interesting things there to discuss. So initially, the first idea to realize quantum anomalous Hall effect in a topological system started from a quantum spin Hall insulator, so a 2-dimensional topological insulator, with 2 counter-propagating helical edge modes. You add magnetism into the mix, so magnetic exchange interaction, and this can effectively reinvert band structure for one of the 2 spin species back to the trivial regime, effectively killing one of the 2 modes, leaving you with a single chiral mode, which realizes quantum anomalous Hall effect. Now, that being the case, one could reasonably assume the effect is 2-dimensional, because you start from a 2-dimensional topological insulator. And then if you think about the scaling of conductivity tensor elements, so the so-called flow diagram, you would expect to see the same kind of behavior as you would see for conventional quantum Hall effect. And indeed, this kind of scaling was observed for quantum anomalous Hall effect already very early on. But then on the other hand, we have this very famous prediction by Nomura and Nagaosa for a surface state of a 3-dimensional topological insulator, which can be made magnetic. And they basically found that this scaling diagram gets a fractional shift. So it's fundamentally distinct from this 2D case. And this is all intimately related to this half-integer quantization, axion physics. There's a lot of nice things behind it. And if you like buzzwords, axion insulator is often used in the literature, in the papers. Okay, so if you think about a 3D system, what can actually be measured? So for a 2D case, the situation is pretty clear. We can grow a layer which is thin enough to be in the 2D regime. We can pattern it into a device. We can make a transport experiment. We can get the scaling. Easy peasy. Now, for the 3D case, we have a prediction for this cylinder. While interesting theoretically object, it's not something we can create in a lab. So we have to somehow translate it to something we can experimentally do. And what we can do experimentally is a slab of material. So to translate it to something flat, you can make a thought experiment where you expand.
I thought with the action, you had the top surface and bottom surface, so it was integer.
Yeah, of course. It is. In the end, it is. I will get to that. Yeah. So you make a thought experiment, you expand the radius to infinity, and you get something which is flat. Of course, the layer we can create has a finite thickness, so you also have, wrong button, you also have the bottom. Okay. You also have the bottom interface, and if you run the same argument backwards, you find you have second one of those cylinders on the bottom. So now if you can come up with an experiment to flip magnetization on both surfaces simultaneously, you should be able to see doubling of this scaling diagram. So you should see transition from 1 to -1, which I think answers your question. Yeah, so now we have a real experimental observable. For a 2D case, we should see this. When we create a transition from 1 to -1, we should see these 2 semicircles. For a 3D case, for thicker films, we should see something which looks different, which goes directly. Okay, so now we can grow a series of layers with varying thickness and cool these samples to low enough temperature and measure the scaling. Starting from a thinner film, we cool it to low enough temperature, apply perpendicular magnetic field, measure hysteresis loop. This is conductivity sigma xy and sigma xx. You make a parametric plot, and you find that we see these 2 semicircles, as you would expect for a 2D case. And then as we increase the layer thickness, we see transition to something which looks different from the case of the 2D scenario, and rather it looks more like what you would expect for the 3D case. Now, for completeness, what we can also do, we can look at a temperature dependence. And this really exemplifies that these 2 belong to different classes. Because especially if you look at temperature dependence around these special points in the flow diagram, the top of the semicircle, this is known as a singular point. And actually, if you tune the system to this point, you expect to see no temperature dependence. And then this is visible here for the 3D film. It's temperature independent. And then this is when sigma xy equals 0. And for a 2D case, we see the same temperature independence when the sigma xy is equal 1/2. And this is visible here. And this is reminiscent of the semicircle shifting as you go from 2D to 3D case. Okay, so let's get to something on a smaller size scale, because it turns out this material also shows quite a bit of interesting magnetic dynamics. So this material system, it's a perpendicular ferromagnet with very clear inhomogeneities. If you look at a topography of these films, you always find that they are prone to producing rotational twin domains. Now, we know how to get rid of these domains. It's not like we don't know how to grow the material. It's just that when you grow with better and better crystalline quality, for reasons, we don't know why, you lose quantization. So some degree of these rotational twins is necessary, actually, to observe proper quantization. But anyway, the existence of these twins, the boundary between these twins provides a primary source of translational symmetry breaking, and therefore creation of a magnetic domain wall at these boundaries is quite cheap. So the point is this material very easily breaks into magnetic domains. And this was also observed by other groups by direct magnetic imaging, that indeed you get magnetic domains in this 50 to 200 nanometers or so size range. Okay, so the material itself is a single easy axis perpendicular ferromagnet. So it has two stable magnetization directions. It can point up or down. Now, if you look at the potential landscape as a function of an angle, it has two minima corresponding to up and down. And if you put the magnetization in plane, it has higher energy, which corresponds to a potential barrier. Now, if the magnet is instead, say, a single molecule, each of these magnetization directions is a quantum state. And then if the potential barrier is not too high in between, magnetic quantum tunneling is possible. This is a situation where the magnet can tunnel between these two states. Now, if at the same time the magnet is a macroscopic ensemble, so a 50 nanometer domain in this case would have some 10,000 magnetic atoms, this would be an example of macroscopic quantum tunneling of magnetization. Okay, so if you think about magnetic quantum tunneling, what to look for in the experiment, and the answer is switching dynamics. So in the high temperature limit, you expect to see the system going spontaneously back and forth above the magnetic anisotropy induced barrier. And this is basic thermal agitation, a well-known behavior. Now, this thermal activation, this thermally agitated behavior, completely is expected to freeze out at low temperatures, because eventually you don't have enough thermal energy to go above the barrier. So the system should just collapse to one of these two states and just stay there indefinitely, unless there's another channel which goes through the barrier. So actually, if you're in a regime where you expect to see quantum tunneling, you expect to see thermally activated behavior at high temperature, and at low temperature, you expect to see a saturation of the dynamics. And this is, in general, nothing new. This has been observed in many material systems already, like more than almost 3 decades ago. Yeah? These are some examples. They actually plot 1 over temperature, so high values are low temperature, and they observe saturation of dynamics and dynamics speeding up, being thermally activated at high temperatures. These are some examples, some magnetic clusters in gallium arsenide, iron cluster nanomagnets, and domain walls in this lithium compound. And the question, can magnetic domains in a diluted magnetic TI show similar behavior? I will try to convince you that the answer is yes. So to dream about capturing such dynamics in a transport device, we first need to fabricate a device which is small enough to have a small enough area such that the number of domains that can fit in is small. So then we can hope to single out effects of single domains. Here you can see how such a device looks like. We have a 6-terminal device with some 160 nanometers width. This should be small enough. So we take this device, we cool it to low enough temperature. We leave the sample alone and simply record Hall resistance as a function of time. We see 2-level telegraph-like noise. Now, in general, in mesoscopic systems, telegraph noise is nothing unusual, and it has a trivial origin, usually. You can think of a situation where you have a state which can trap and release an electron back and forth, and this will change electrostatically environment of the sample, and it can produce 2-level switching in measured resistance. I will try to convince you this is not the case here, based on how the frequency of this switching responds to magnetic field and temperature. Okay, so we have this telegraph noise. We need to analyze it. We basically let the measurement run long enough to capture a couple of hundreds of those switching events. And from that, we can look at the lengths of these plateaus. And basically, long story short, we can obtain a mean lifetime in each state. So average length of the plateau. And then we can see how these lifetimes respond to magnetic field and temperature. Okay, if we go with the interpretation that it's the magnetic domain which is switching up and down, back and forth, it's reasonable to assign a state with larger RxY to a domain magnetization aligned parallel to the background magnetization. So we have more than one magnetic domain in the sample, and when the domain is in the same direction as the background, it's adding to the total Hall signal. And then if the domain is pointing in opposite direction, it's subtracting from the Hall signal. Yeah, so let's see how this switching changes with external magnetic field. So here you can see the lifetime of each of these two states in some magnetic field range. And yeah, a couple of things to note. Both magnetization states of the domain can be tuned relative to each other. They can actually cross at some point. External magnetic field promotes the magnetization state pointing along the field, such that when you apply large enough external magnetic field, the state with magnetization pointing along the field has a longer lifetime, which also intuitively, I would argue, makes sense. And we also find that external magnetic field reduces the potential barrier height. This, I think, intuitively also can be well understood. As the magnetic field gets bigger, it should be easier for the domain to flip along the magnetic field. Okay, so let's look at the temperature dependence. So in this same magnetic field range for a couple of different magnetic field values, at the high temperature range, by high temperature I mean above 300 millikelvins or so, we see these dashed lines, which is thermally activated behavior, which is what you expect for a behavior when the domain is going above this magnetic anisotropy-induced barrier. Now we go to the low temperature limit, we see the saturation and dynamics reminiscent of the magnetic quantum tunneling. Now, a few things to note. Below 300 millikelvins or so, so where we see the plateau, we still observe changes in electrical transport response from the sample. So despite the dynamics being, I'm not showing it here, but despite the dynamics being saturated, we still see sample reacting to changes in temperature. So this is not some sort of artifact of us not being to cool down the sample below 300 millikelvins. So it looks like the plateau is real. And also we can look at the value of the plateau, which gives us the tunneling rate, compare it to the thermal activation energy extracted from the high temperature data, which gives us the size of the barrier. And we find that tunneling rate changes exponentially with the barrier height, which also, I would argue, intuitively makes sense, as to a first order wave function is going to penetrate exponentially into the barrier, so the tunneling rate changing exponentially also makes sense on some level. Now, while interesting, we need to keep in mind this magnetic noise is always present in the sample. This gets very strongly and quickly suppressed as we increase the device size. And this is easy to understand because the bigger the device, the more domains inside. And if a single domain is flipping, then your macroscopic Hall bar does not care about it. So here you can see some perpendicular magnetic field sweeps for, this was the studied device I showed you. Then we have 200 nanometers, 1 micron, 2 microns. So at 2 microns, we already see behavior which is pretty much the same as for bigger, even macroscopic Hall bars. So the point is that for large metrologically relevant devices, which are even 2 orders of magnitude larger, this is unlikely to be relevant. Okay, so now let's get back to larger devices and to some metrology. How precise is the quantization? So to answer this question, we teamed up with the German National Metrology Institute, Physikalisch-Technische Bundesanstalt, PTB for short, and specifically with the group of Hans-Jörg Scherer, where they specialize in precise measurements of the quantum Hall effect using proper metrologically traceable methods. And yeah, so in this experiment, the sample is again placed in the dilution fridge at temperature of 30 millikelvins or so. And yeah, this is a bridge geometry. And if you can ensure that these two currents have well-defined values, you can measure voltage over the bridge, which will give you a deviation of your sample resistance from a calibrated reference resistor. And at the heart of the setup is a so-called cryogenic current comparator. It's a elaborate device which allows you to very precisely balance these two currents. And the way this is done, these two wires run inside of a superconducting shield. The two currents you want to compare, they flow in opposite direction inside of this shield. The difference between these two currents creates a magnetic flux. The magnetic flux creates a screening current on the superconductor. The screening current on the superconductor again creates magnetic flux, and this is picked up by a DC squid. So a squid acts as a null detector to adjust one of the power supplies to balance the current properly. Again, if you're curious about more details, you can look up this archive we put up recently. But using these tools, we can very precisely measure quantization in these devices. And without going into details, because this involves a lot of cumbersome uncertainty analysis, again, everything is outlined here in this paper if someone is curious about technicalities. But what we can say is that the Hall resistance of the quantum anomalous Hall insulator is quantized to h/e² to within a few parts per billion, or 10 to minus 9, relative uncertainty, and importantly at 0 external magnetic field, which is what we want. It's also worth noting that our colleagues from Japan achieved a similar precision in their chromium-doped BST sample, albeit at a small external magnetic field. But nevertheless, this shows that the effect is nicely universal and reproducible. And this is precisely what you want from a standard. Okay, so this is nice as a proof of concept. This is already good enough to call it a quantum resistance standard if you just look at the numbers. But of course, it works under very extreme conditions. So 30 millikelvins and also very small currents. By small, I mean 100 nanoamps or so. This is quite small by metrology standards. Of course, in metrology, you want to push as much current as you can to get better signal-to-noise ratio. And to give you an idea, conventional quantum Hall standards that rely on graphene, they can operate at a few tens of microamps. So there's quite a bit of way to go to improve this. So let's talk about this now. Measurement current and temperature. These are two main problems. Starting with the measurement current, the primary breakdown mechanism, which breaks down the effect, is a result of voltage between the edges. So if you look at a Hall bar, you apply a bias voltage to the top contact, you ground the bottom contact, you find that one edge is at high voltage and the other edge is at low voltage. This is simple Landauer-Buttiker. And as you increase the measurement current, the voltage between the edges increases, and eventually it exceeds a certain threshold such that electrons can backscatter to the opposite edge, and you measure abrupt breakdown of the effect, or breakdown of the quantization as measured in the experiment. So how we can combat that? One way would be to go away from a Hall bar and move to something which is closer to a Corbino geometry. So the traditional Corbino has a single inner contact, and then there's the material in between which you want to study, and then there's one outer contact. What we do instead, we have multiple contacts along each perimeter. Now, we call this multi-terminal Corbino, but if you're familiar with old quantum Hall literature, at least the inner part of this device is completely equivalent to something which is known as inverted Hall bar. But nevertheless, what is important here is we have an edge state going on the inner perimeter, edge state going on the outer perimeter, and it's separated by an insulating bulk. So what we can do, we can take advantage of that fact that these two circuits are independent. We can independently electrically bias each of the two, and we can do it in this way, for example. So what we do here is we apply a bias voltage to this contact on the outer perimeter, and we ground this contact on the outer perimeter, such that this part of the perimeter is at high voltage, this part is at low voltage, and along the inner perimeter we do the same but reversed, 180 degrees. So we apply a bias voltage here and we ground here such that this part is at high voltage and this part is at low voltage. And if you look at the colors, you find that the two edges which always run next to each other, they're either both at high voltage or both at low voltage. So this electric field buildup should be avoided, or at least massively suppressed. Okay, so to test it, we need a device which can do that. Here you can see how such a device looks like. We have multiple contacts on inner and outer perimeter. We also have a top gate to tune the sample into the middle of the plateau. Yeah, so now we cool this sample to, again, 30 millikelvins. And first we do control experiment without any balancing. So for this, we inject current into the outer perimeter between contacts A and C, and the inner perimeter simply remains grounded. So as you increase the measurement current, the voltage between perimeters is increasing proportionally. So this simulates what happens on a hall bar. You can measure in this geometry hall resistance as well. So in this case, current is flowing between A and C, and we can measure voltage drop between B and D. This is perfectly equivalent to a hall bar, to a hall measurement. And yeah, here you can see how such signal looks like as a function of current. It's at low bias, it remains quantized, and then there's an abrupt breakdown above a specific threshold. For completeness, we can do the same with longitudinal resistance. We find that it's 0 at low bias, and then abruptly it breaks down. Now we do the same with balancing. So in addition, we source a current to the inner perimeter to ensure that these voltages or electrochemical potentials are balanced, and we indeed find that this threshold is eliminated. Now, this is quite promising, I would say, but what is still ongoing is proper metrological tests. We do not know yet how well this performs with proper cryogenic current comparator-based measurements. So basically how flat this bit really is and how much it improves performance at the metrological level. It's not a plug-and-play measurement because it needs to deal with two current sources and two grounding points on the circuit. So this requires some adaptation, but this is very much ongoing. And yeah, we hope to get some results soon. Okay, so last part I want to discuss is the problem number 2, which is the breakdown at very small temperatures. It turns out that to see this proper metrological level of quantization in these samples, you have to be below something like 50 millikelvins. And at the same time, we know that these materials are ferromagnetic up to a few tens of kelvins. So Curie temperature is a few tens of kelvins. And there is no obvious reason why there should be 2-3 orders of magnitude discrepancy between these two temperature scales. And the important question is, does the topological state survive at these high temperatures? Even though we do not see directly the quantization. And I will try to convince you the answer is yes. The edge states are still there. They're very happy. There are just some issues with the device, which I will discuss. It's also worth noting that there's other literature out there also showing some degree of evidence that the edge modes indeed survive at higher temperatures. Yeah, so what do we do here? We make a non-local measurement. Again, we use the same Corbino-like device. We apply a bias voltage to contact A. We ground contact 1. And then we record voltages at all the remaining contacts. And we see how these voltages change with gate voltage and with temperature. So here you can see a couple of gate sweeps with all these individual potentials plotted. 25 millikelvins, half a Kelvin, 1 Kelvin, 4 Kelvin, 12, 14. Then we have a Curie temperature of some 18 kelvins or so. And then we have 21 and 25. We see that above Curie temperature, something abrupt happens. All the potentials are, well, equipotential. All the leads reach the same voltage, as you would expect, because above Curie temperature, you would not expect to see any chiral edge transport anymore. And below that temperature, we see some quite interesting non-local signals. And there's a few things to note here. There's evident chirality in the system. So if you look at the order at which these potentials are arranged, it's B2, C3, D4. So if you look at the schematic here, it's B2, C3, D4. And of course, if you flip magnetization in the layer, this order flips, as you would expect for opposite chirality. But what this is reminiscent of is that the current enters the device from contact A and it turns left. It flows along the edge and it's allowed to backscatter to the inner edge. So this is what would explain these kind of signals. Now, there is a potential difference between the outer and inner perimeter around the entire ring. So B is always above 2, C is always above 3, D is always above 4. This is also screaming edge states. There are rather large non-local signals, so something is pushing the current around the ring instead of flowing directly between these two contacts. I mean, this picture does not show the scale of the real device. This path is really significantly longer than this one. So any trivial bulk current is just going to flow directly here. So something is pushing the current around the ring. And what is pushing it? The edge channels give by far the simplest explanation. What we can also do, we can simulate these signals using Landauer-Butiker-based model, where in addition to having a chiral edge mode on the outer and inner perimeter, we allow for scattering between these two edges by having parasitic bulk conductance. So what all of this tells us is that the breakdown looks like it's a purely technological problem. It's just that we need to make the bulk of the material insulating enough to have nice quantization at higher temperatures. So the relevant parameter is the bulk resistivity between the edges. This, for some reason, breaks down above 50, 100 millikelvins or so. Nobody really knows why, but that is so. OK, this would be it from my side, a couple of take-home messages. I hope I have shown you that vanadium or chromium-doped BST material provides a rich playground for some interesting physics. There's really a lot of topics I have not touched. The quality of quantization is good enough for proper metrology. The topological state is robust against temperature. So the limitations appear to be purely technological. So if we can make somehow bulk more insulating, we should be able to build a standard at 4 kelvins. That's the bottom line. We have no idea how to do it, but at least in principle, it should be possible. There's nothing fundamentally preventing it from being doable. And then the limitations on measurement current can be overcome by double perimeter voltage balancing. Here is more people involved in some of these results, and for more pillow reading on magnetic TIs and Quache from us, you can look at some of these references. Thank you.
So, thank you, speaker. Thank you.